This question says, how are the products of the following reaction related to one another? So we have a monosubstituted alkene as our starting material, which is important. And we also have a two-step reaction that involves reagents that bring about an addition reaction, specifically a hydration reaction. So let's go ahead and think about the different products that are going to be formed here. And let's also consider regiochemistry and stereochemistry. So for our alkene, we are going to focus on the 2 carbons of the alkene. All the other carbons aren't being dealt with. They just kind of come along for the ride. They're not impacted by the reaction. A couple of key things to keep in mind. This is a oxymercuration demercuration reaction. Okay, so in those reactions, it's important to remember that there are no rearrangements. It's one of the key things that distinguishes this reaction from acid catalyzed hydration. Another thing to keep in mind is we have Markovnikov regiochemistry. That's important because it means we're going to add to the more substituted carbon of our alkene. Okay, lastly, we have anti-addition. All right, so kind of 3 key things to keep in mind for this reaction. Because the alkene is flat, we can add our mercury to either the top face or the bottom face. So we can end up with kind of 2 different stereo products because of that. So the products that we make in this reaction look like so, where we add our OH to the more substituted carbon, and then a hydrogen gets added to the less substituted carbon. The OH group can either be wedged or it can be dashed. Again, we see both because the alkene is flat and the oxymercuration demercuration can take place on either the top face or the bottom face. All right, we don't really have to worry too much about the anti-addition in this example because the hydrogen atom is added to a carbon that already has hydrogens. So we don't necessarily have to show that anti-stereochemistry in our products. We just know that it's there. All right, so our 2 products are alcohols. And this question is asking how are they related to one another? Our answer choices are showing us that they want us to think about this in terms of isomers, stereo or constitutional isomers. They're not going to be constitutional isomers because the molecular formulas of these 2 molecules are identical. They also have the same connectivity, right? So the real question is, are they identical? Are they enantiomers? Are they diastereomers? We know that they're not identical because one has a wedged OH here and one has a dashed OH here. This molecule these 2 molecules are going to be related to each other, and that one carbon has opposite stereochemistry and the other carbon has the same stereochemistry. So if we look at the second carbon here, the one that just came along for the ride that doesn't get impacted, that one stayed the same. All right, so these 2 molecules are not going to be mirror images. They can't be mirror images because the methyl is wedged in both cases. All right, so we can cross off enantiomers. We know they're related, and so last choice is diastereomers. Diastereomers is a catch-all category for molecules that are stereoisomers, but not mirror images of each other. And we see diastereomers most often when there's 2 or more carbons or when you have cis-trans isomers. So here we have 2 or more chiral carbons, 2 or more chiral carbons, and there's no plane of symmetry in this molecule. So we know that they can't be meso. So that means they're diastereomerically related to one another by being diastereomers.